Sir, cloud
हाँ
recording.
हो गया. Yes, yes. Good morning
चलिए
all.
now start. Yes, sir.
Welcome to the current session on 27th of May. So we are into our third week of the summer program on additive manufacturing in or 3D printing technology in manufacturing and infrastructure. So we have of interesting sessions in the past, and also very interesting sessions are scheduled both from internal faculty as well as from external experts. So today's session will be taken by Mr. Gaurav Sharma, who is a faculty member, Department of Mechanical Engineering, IILM Engineering College, Greater Noida. He is pursuing his PhD from IIT Indian School of Mines, Dhanbad, which is a very reputed institute, and he will be pursuing PhD work in the area of solar thermal or solar photovoltaic. So he has been teaching the subject of thermodynamics and heat transfer. So he has good control over the subject. So now I request Gaurav to take over the session. Thank you.
Okay, thank you, sir. Okay, thank you, sir. Let's start. I hope my voice audible and my slide is visible. Today
Yes, sir.
topic
This is audible.
today topic is 3D printing in solar system and heat exchanger. Next, these contents are basic of solar system and 3D printing and the power industry, how technology is transforming the sector 3D printing in the solar power industry, 3D printing in the wind power industry, 3D printing batteries, 3D printing in conventional power generation, and 3D printing in the nuclear power industry. Next, 3D printing in the power industry, screen printing to 3D printing of solar cells, history of printing technologies for solar cells, screen printing to 3D printing of solar cells, and what is 3D printing in heat exchanger and application. And start basic of solar system. सबसे पहले बेटा बेसिक पता होना चाहिए कि हमें बेसिक है क्या, ये सोलर सिस्टम है क्या चीज. तो व्हाट इज सोलर एनर्जी. सोलर एनर्जी एनर्जी की बात करते हैं. आपने पढ़ा होगा बेटा हीट एंड मास ट्रांसफर सब्जेक्ट पढ़ा होगा. व्हाट आर दी मोड्स ऑफ हीट ट्रांसफर. देयर आर 3 टाइप्स ऑफ मोड्स ऑफ हीट ट्रांसफर. फर्स्ट इज कंडक्शन, सेकंड कन्वेक्शन, थर्ड इज रेडिएशन. मेन जो इंपॉर्टेंट है बेटा सोलर सिस्टम इज रेडिएशन. रेडिएशन क्या होता है. व्हाट इज रेडिएशन. रेडिएशन इज ए मोड ऑफ हीट ट्रांसफर in which does not require any material and medium, hence electromagnetic wave propagation with the speed of light. इसमें क्या है बेटा किसी भी मीडियम की जरूरत नहीं होती है, डायरेक्टली हीट ट्रांसफर होता है. और पढ़ा होगा आपने कंडक्शन और कन्वेक्शन. कंडक्शन और कन्वेक्शन में क्या होता है, जो भी हीट ट्रांसफर होगा इसके ये मीडियम के थ्रू हीट ट्रांसफर होगा. अब देखो रेडिएशन की बात करते हैं. रेडिएशन में क्या होगा, डायरेक्टली हीट ट्रांसफर होगा. जैसे एग्जांपल सन टू अर्थ. सन से जो एनर्जी निकल रही है किस पे पड़ रही है, अर्थ पे पड़ रही है, डायरेक्टली हीट ट्रांसफर हो रहा है. अब देखो सोलर एनर्जी है, एनर्जी क्या है आपने पढ़ा होगा थर्मोडायनेमिक्स. थर्मोडायनेमिक्स क्या है बेटा, थर्मो प्लस डायनेमिक्स इज इक्वल टू थर्मोडायनेमिक्स. थर्मो मींस इज प्रेशर, टेम्परेचर्स, एंथैल्पी, एंट्रोपी, एंड डायनेमिक इज मोशन, प्रेशर और टेम्परेचर का मोशन. It is called thermodynamics, and thermodynamics is the science of energy in its effect on the property of the system. It is called thermodynamics. And पढ़ा होगा system, surrounding and extensive property, intensive property. तो ये सारी चीज क्या है बेटा, एनर्जी है. अब जो स्टार्ट करते हैं व्हाट इज सोलर एनर्जी. सोलर एनर्जी क्या है. सोलर एनर्जी इज रेडिएंट लाइट एंड हीट फ्रॉम द सन that is using a range of technologies such as solar heating, photovoltaics, and solar thermal energy, and solar agriculture, molten salt power plants, and artificial photosynthesis. And it is essentially source of renewable energy, and its technology are broadly characterized as either passive solar, active solar, depending on how they capture and distribute solar energy or convert it into the solar power. Active solar technique include the use of photovoltaic system and solar power and solar water heating to the energy. Passive solar techniques include a building to the sun, selecting materials with favorable thermal mass or light properties, and designing space that naturally circulated air is solar energy. Next, but a difference between renewable energy and नॉन renewable energy. सबसे पहले आपको इस क्या बेटा सोलर पता पड़ गया, सोलर के पार्ट्स कौन से हैं, इसके डिवाइड किया गया रिन्यूएबल एनर्जी, नॉन रिन्यूएबल एनर्जी. रिन्यूएबल एनर्जी क्या होती है, नॉन रिन्यूएबल एनर्जी क्या होती है. जैसे ये आप रिन्यूएबल एनर्जी क्या दे रखे हैं बेटा, इस बायोमास एनर्जी, सोलर एनर्जी, एनर्जी फॉर्म है विंड एनर्जी, जियोथर्मल एनर्जी, हाइड्रो पावर एनर्जी. And non-renewable energies coal, natural gas, nuclear fuel and fuel oil, that is called non-renewable energy. And renewable energy, renewable energy, these sources which are used from the starting of human life, and these resources for lighting purpose, transportation and cooking, heating from wild animals, etc. and renewable sources या renewable energy जो दे रखे बेटा renewable energy are also called as non-conventional source of energy. Non-conventional source of energy. What is biomass energy? Biomass is plant or animal material used for energy production. Energy production is electricity or heat, or in various industrial processes as raw substance for a range of products. It can be grown energy crops, wood or forest waste from food crops. And food processing, corn crops, animal farming. Animal farming is manner rich in nitrogen and phosphorus or human waste from savage plants. That is called biomass energy. Next is wind energy. What is wind energy? Yeah, wind power. Wind energy is the use of wind to provide the mechanical power through wind turbines to turn electric generators and to do other work like milling or pumping. And wind power is a sustainable and renewable energy and has a much smaller impact on the environment compared to burning fossil fuels. That is called biomass, wind energy and wind power. Next is geothermal energy. What is geothermal energy? Geothermal energy is thermal energy generated and stored in the earth. Thermal energy is the energy that determines the temperature of matter. The geothermal energy of the earth crust or from the original formation of the planet and materials in the currently but possible roughly equal. That adjective geothermal organized from the Greek roots and meaning earth, meaning hot. Next is hydropower energy. Hydropower energy is also called water power. And hydro the energy of falling or fast running water which may be harnessed for useful purpose. Since ancient times, hydropower from many kinds of water mills has been used as renewable energy source for and the operation of various mechanical devices such as textile mills and trip hammers, dock cranes and domestic lifts and own mills. which produced compressed air from falling water, is something used to power other machinery at a distance. In the late 19th century, hydropower became a source for generating electricity. The first house powered by hydroelectricity in 1878. And the first commercial hydroelectric power plants was built at Falls in 1879. In 1881, street lamps in the city of Falls were powered by hydropower. Next is non-renewable energy. Renewable energies are biomass energy, solar energy, wind energy, geothermal energy, and hydropower energy. And non-renewable energy: coal, natural gas, nuclear, fossil fuel, oil. What is coal? Coal is a black or rock formed as a rock called coal seams. Coal is mostly carbon with variable amounts of other elements and hydrogen, sulfur, oxygen, and nitrogen. Coal is formed when that plant matter into peat and is converted into coal by the heat and pressure of deep. Over millions of years, deposits of coal organized in former called coal that covered much of the Earth's typical land areas during the late Carbons and time. Next is natural gas. Natural gas is a naturally hydrocarbon gas mixture consisting primarily of methane, but commonly including varying amounts of other higher and sometimes a small percentage of carbon dioxide, nitrogen, hydrogen, or helium. It is formed when layers of decomposition plant and animal matter are exposed to intense heat and pressure under the surface of the earth over millions of years. The energy that the plants originally obtained from the sun is stored in the form of chemical bonds in the gas. That is called natural gas. Next is fossil fuels and oils. Fossil fuels are hydrocarbons, primarily called fuel oil or natural gas, formed from the remains of dead plants and animals. In common, the terms fossil fuel also includes hydrocarbon containing natural resources that are derived from animal or plant sources. Next, what is solar panel? अब बेटा नेक्स्ट ही स्लाइड होता है जो सोलर एनर्जी है. सोलर एनर्जी में क्या हुआ, दैट देयर आर टू टाइप्स के होते हैं, रिन्यूएबल एनर्जी, नॉन रिन्यूएबल एनर्जी. अब नेक्स्ट स्टार्ट होता है इज आपका इज व्हाट इज सोलर पैनल. Solar panel, what is solar panel? The term solar panel is used for a photovoltaic module. A PV module is an assembly of photovoltaic cells mounted in a framework for installation. Photovoltaic cells use sunlight as a source of energy and generate direct current electricity. A collection of PV modules is called a PV panel. What is PV? PV is photovoltaic. PV panel and a system of panels is an arrays. Arrays of a photovoltaic system supply solar electricity to electrical equipment. Next, printing solar panels is small videos.
The future of solar energy depends on a union of new and old technologies. If photovoltaic or PV devices that turn light into electricity could be mass produced with printing presses, as if they were newspapers or banknotes, they could be affordable and ubiquitous. Conventional silicon-based solar panels are rigid and bulky. Small, thin and flexible devices on films are already being made that are lightweight and translucent. These use little material and can generate electricity in low light even indoors. Integrating them into phones and watches, as well as walls and windows, would transform the world's energy generation, reduce pollution, and mitigate climate change. Yet flexible solar panels face several hurdles. Some are based on harmful substances, such as heavy metals, and their manufacture uses hazardous solvents. Others are quick to degrade and inefficient in converting light to electricity. Printers used in the publishing, computing, and electronics industries struggle to print PV materials that need to be built to nanometer precision over many square meters. For all these reasons, printable solar cells are yet to find a foothold in electricity markets. Currently, most research and development investment goes into conventional silicon solar cells, which account for more than 90% of global production. Yet manufacturing these uses a lot of energy. It's been estimated equivalent to around 10% of the cell's entire lifetime output. Printed solar cells won't become widespread until they're cheaper and safer to make. Researchers and businesses must work together to improve the efficiency, environmental impact, and stability of these cells, and also to scale up their manufacture and plan their market deployment. Now, the PV panel generates is proportional to the surface area exposed to sunlight. Globally, we consume around 20,000 terawatt-hours each year. Meeting this need will require enough PV devices to cover an area of 100,000 square kilometres, or an area the size of Iceland. Production globally is yet to be achieved at this level. Printed PV devices are typically made from many layers of material on a substrate of conductive glass or plastic. Each layer is a function. Semiconductors or sanitizers absorb visible light, and other materials carry electric charge to electrodes. Many types of printed PV devices are being developed. Some feature organic semiconductors, such as polythiophene. Others use light-absorbing dyes, and another substrate contain quantum dot solar cells or nanoparticles that absorb light. The most efficient, though, are the perovskite-based cells. The latest version of these convert 22% of the solar power to electrical power. This is more efficient than solar cells made from multicrystalline silicon, but yet they can't currently be rolled out commercially because they degrade under high humidity and heat. Furthermore, printing layers that are nanometers to micrometers thick uniformly without pinholes over many square meters is exceptionally difficult. The electronics industry commonly uses screen printing, feeding a paste through perforated screens, but the layers in printed circuit boards are hundreds of times thicker than those of PV devices, and turning materials into viscous paste alters their physical and electrical properties. Other techniques for printing PV devices have been demonstrated in the lab over areas of around 10 square centimeters. These include a ink slip, slot die printing, spray coating the substrate, passing the substance over a rotating cylinder, and moving a blade of the substrate to ensure a consistent supply. Sadly, each technique has its downsides. In slot die printing, for example, the spacing of patterns is hard to control, and gaps reduce the active area of a panel. In gravure printing, contact between the printed substrate can damage the underlying layers. Such drawbacks mean that currently the printed solar cells are less than half as efficient as the best non-printed equivalents. To print thin, pinhole-free layers over more than 1 square meter will require an intelligent, more precise equipment and laser processing technique. Clearly, therefore, an alternative attractive approach would be to develop PV materials that work with existing industrial printing methods. For industrial scale printing, this involves materials that can be formed into light, liquid solutions or pastes. For PV devices, this means either using solutions of chemicals, polymers, dyes, and such like, or dispersions of nanoparticles, such as quantum dots. But many of these degrade over days to weeks if not properly sealed. More stable alternatives, such as silicon, are far harder to print. A balance must also be struck between the efficiency of the device and the environmental impact of its manufacture. The most efficient thin film solar cells include toxic or rare materials such as cadmium and lead, as well as hazardous organic solvents. Indium, another rare element, is a common ingredient in transparent conductive films of PV devices. Its use is expected to rise over the coming decades. However, depleted mineral deposits and low rates of recycling threaten to exhaust indium stocks before the end of the century. Researchers therefore are looking to ways to use abundant materials that can be processed in solution to make efficient devices with little toxic waste. For example, carbon-based electrodes and layers of less precious metal. Again, though, we come back to the problem that at present such designs are often less efficient than the current deployed silicon-based technology. Where does this all leave us then? Frankly, what's next? Well, the huge success of silicon panels has become a hurdle for emerging technologies. Manufacturers of silicon-based PV devices share materials, equipment, and practices, crippling issues such as cost. On the flip side, developers of printable devices are isolated, and the maturity of the silicon industry means there's little urgency for further. Consequently, capital investment and product commercialization are perceived as risky, given that printable PV devices are still in development. And government funding, therefore, is needed to catapult such devices into competitive states at the decline of the silicon PV industry. And market penetration, therefore, should develop in stages. Early printable PV devices should target weaknesses in the current silicon-based technologies. Think here of the poor performance in low light and lack of polarization. The next wave, therefore, should complement silicon solar cells and ideally integrate with them. For example, silicon perovskite devices would harness a greater generation of incoming solar light than the silicon devices alone. If printing technologies can capture just 5% of the PV market, their advantages should ensure they play an ever-increasing part in meeting global demands for renewable energy.
So this video is printing solar panels for next generation. And next is theory and construction of PV system. PV is photovoltaic module. Theory is from a solar cell to a PV system. Then solar cell is connected to solar module, and then is solar panel. And this raised arrays is solar arrays. And PV system is our electricity meter and fuse box, inverter, battery, charge controller, generation meter, and DC isolator. Hello. Hello.
Yes, sir.
Hello.
Yes, sir.
Hello.
Audible, sir. Audible.
Audible. And slide visible?
No, sir.
Visible?
No, sir. Yes, sir.
Okay, okay.
Yes, sir. Visible. Yes, sir.
Visible and third,
Yes, sir.
so
Yes, sir.
my slides visible.
Yes, sir.
Yes, sir.
Visible, sir.
Hello. Hello.
Yes, sir.
Madam, slides visible, not visible.
Not visible.
Not visible, sir.
Not visual, sir. Visible, sir.
Okay,
Visible.
okay.
Now visible, sir.
Okay, okay. Thank you. Cells must be, solar cell must be protected from mechanical damage and moisture. Most moisture are rigid but semi-flexible ones based on thin film cells are also available. They, these cells are connected electricity in series, one to another to the desired voltage and then in parallel to increase the wattage of the module is the mathematically product of the voltage and the of the module. The manufacturing of the specification of solar cell and solar panels are obtained under standard condition, which is not the real operating condition the solar panels are exposed to on the installation. And PV junction, PV is photovoltaic. A photovoltaic PV junction box is attached. PV is attached to the back of a solar panel, back of the solar panel, and functions as its output interface. External connection for most photovoltaic modules use MC4 connections to facilitate easy waterproof connection to the rest of the system. A USB power interface can also be used. Module electrical connection are made in series to achieve a desired module electrical connection are made in series to achieve a desired output voltage or in parallel to provide a desired current capability amperes of the solar panel or the PV system. The conducting wires that take the current of the modules are sized according to the may contain silver, copper, or other non-magnetic conductive metals. Bypass diodes may be incorrupted or used extremely in case of partial module shading to maximize the output of the module section steel. Some special solar photovoltaic modules include in which light is focused by lenses or mirrors, smaller cells. This enables the use of cell with a high cost per unit area in a cost effective way. And solar panel also use metal frames consisting of raking components, reflector shapes, and to better support the panel structure. And this is theory and construction. Next. Next, 3D printing and the power industry. Power industry, how technology is transforming the sector. What is 3D printing? What is 3D printing or additive manufacturing is the process of joining materials to make objects from three-dimensional model data, usually layer upon layer. This is data by Global Data Energy. In 2017, the 3D printing industry was worth $7 billion, up from $3 billion in 2013. And by 2025, it is expected to account for over $20 billion all over the world. And in additive manufacturing has found its application in different sectors of the power industry, both in building prototypes and in mainstream production, leading to process simplification or operational efficiency. Additive manufacturing can produce components with complex geometries, consume raw materials, produce less waste, have reduced energy consumption, and decreased time to market. With the power industry under pressure, manufacturers are turning towards additive manufacturing for solution with reduced cost and shorter time frames. During the initial phase of marketing inroads in the power industry, 3D printing has achieved a fair level of success with the power industry and technological firms creating and for the benefit of each other. Next, 3D printing in the solar power industry. This is data, global energy data. Through technical feasibility of solar cells has been proved long back, the capacity factor, CF is capacity factor, is still low with an average of around 70%. In best case scenario, the low capacity factor of the solar panel makes it difficult to attain economics of scale for large solar plants and therefore requires for operation over a period of time. 3D printing can be a game changer in this respect as it is now being used to create solar panels. Although the technology is at a very stage, researchers claim that application of additive technology in solar panels could reduce manufacturing cost by 50% with 20% increase in efficiency. Compared to traditional solar panels, 3D printed solar panels are light, super thin solar strips which can be easily transported anywhere with reduced chances of damage. In Australia, the Commonwealth Scientific and Industrial Research Organization used industrial 3D printers to print rolls of solar cells in the form of A3 sheets, which can be used on the surfaces of windows and buildings and function as efficient solar panels. The scientists developed a photovoltaic ink to be used on the flexible plastic strips. In another instance, the Australian Solar Thermal Research in partnership with the Commonwealth Scientific and Industrial Research Organization developed a solar plant where the entire solar field in 3D printed. Next, printing solar panels in the backyard video. This is small videos for solar panel in the backyard.
Time to make some room on your wish list. If you thought a 3D printer sounded good, how about this? A machine that prints solar panels. This is one of its creators.
My name's Sean Frame. I write inventor when I go through customs.
And Sean was kind enough to let me live this DIY dream by bringing a few pieces of his prototype to my backyard.
Yeah, this is about one half of a complete solar pocket factory.
The other half didn't fit in the suitcase.
That we smuggled over into New York City, direct from Hong Kong and Manila.
That's where Sean's colleagues are based. They're self-identified independent inventors who team up to make stuff, sometimes financed by big companies, and sometimes, like with this project, bankrolled by strangers.
We're launching this on Kickstarter, and as of this shooting, we're at about 70K, and this is meant to pay for some of the equipment required for a solar pocket factory.
The aim is to have a full working model done by April, and then they have this other modest goal.
Hopefully revolutionize how microsolar production happens in the world.
Currently, mini solar panels like
The 2-volt panels that go in your garden lights or the power your iPhone
are made by hand in factories in China, India, and Bangladesh, Sprain says. Assembly line workers take laser-etched silicon cells, that's the stuff solar panels are made of.
A bunch of people snap off little tiny pieces of the silicon and you combine them together. The problem is that labor prices are going up and the price of silicon has plummeted over the last couple years.
So small panels end up being much more expensive per watt than large-scale panels, Sprain says. He says that automating the process could bring down the price. Enter the solar pocket factory. You would start by feeding sheets of silicon into this module.
This one here replaces this step of snapping the laser scored cell into solettes.
In the full prototype, the machine will catch the solettes and bring them to this module where they're attached to a vacuum.
This device does the placement and the interconnection of the solettes. The solettes are pushed up each piece of silicon outputs around 1/2 volt. Light comes in, a photon dislodges an electron that hops to the other side of the solar cell. And then there's enough that jump over to the other side that there builds up almost an electrical pressure voltage.
And voila, you have electricity. And it turns out that you can take a bunch of these little solettes and wire them up in series to get the micro power output you want.
The bottom of the solettes are positive. One solette to the top of a neighboring solette. So we're going positive to negative, just like you would 4 batteries to get, 5 volts.
So far, supergluing the solettes in a shingle pattern seems to work. In the full model, the panel will get a protective coating, will be baked in an oven, and then a testing device will make sure the panels work. And then they'll be ready to go.
The goal in April is that we can do 1 placement per second. It means a machine can do between 300,000 to 1 million panels per year, depending on the mix of voltage.
Although the solar pocket factory fit in my backyard, the model is more like
the microbreweries. They're not things that people necessarily have in their homes, but they're down the street and in their neighborhoods.
And the idea is that if people can get micro solar panels more easily, Crane says, maybe more inventors will use them. It's a supply drives demand kind of argument.
Solar pocket factories combined with maker bots, combined with shop bots, we think could maybe push more and more solar products out into the world. This is speculation.
Next, 3D printing in the wind power industry. What is wind power or wind energy? Wind energy is the use of wind to provide the mechanical power through wind turbines to generators and traditionally to do other work, drilling or pumping. Wind power is a sustainable and on the environment compared to burning fossil fuels. And this is wind turbine, wind energy, and main components of the wind turbine. This is numbering is one is foundation and 2 connection to the electric grid, and number 3 is tower. This is tower, and next 4 is X is ladder, and fifth is wind orientation control. This is wind orientation control. And next 7 is generator, and 8 is anemometer, 9th is electric or mechanical brakes, and 10th 10 number is gearbox, and 11 is rotor blade, 12 is blade pitch control, 13 this is rotor hub. This is main components of the wind turbine. 3D printing in the wind power industry. Development and innovation through materials and manufacturing technologies are essential for the wind industry and to continue increase its annual energy production. Additive manufacturing could in the future enable inside manufacture of turbine components that are designed for the unique needs of the resources of a particular location. Also, additive manufacturing provides a tool to make up for the demand and supply for wind turbine. Spare parts is continue models for which the manufacturer will have limited quantity to meet the repairs. And the US Department of Energy Wind Program and Advanced Manufacturing Office has partnered with public and private organized to apply additive manufacturing in the production of wind turbine blade module. Traditionally, blade design requires the creation of a plug of full-size representation of the final blade, which is then used to make the module. This is one of the most time-consuming and labor-intensive process in wind blade construction, where 3D printing can save these critical resources. Another potential benefit is that large wind blade would not have to be carried over long distances. Instead, the 3D printer could be taken on site and print the blades, thereby saving transportation costs. Also, this would cut down the manufacturing time of the mold by 35%, making it possible to combine different materials in different area of the blades. This is 3D printing in the wind power turbine. This is data, global data. And next is 3D printing in the wind power industry is small videos of wind turbine. Next, 3D printing and batteries. Research teams all over the world are 3D printing technologies to create complex internal structure of the batteries with increased capacity and flexible in shape and size. In UK, founded by the Engineering and Physical Science Research Council, has taken up a project to develop a new kind of energy storage system using a conductive light the desktop printer capable of printing the graphite with the high electrical and thermal conductivity. What is thermal conductivity? Thermal conductivity depends on the material. And can easily outperform graphite commonly used batteries. A team from Harvard University is also developing and version of Leon battery with the use of 3D printing. The micro batteries whereby accurately printing stacks of different high enable and development of powered mini electronics, robots, medical implants, and more. Researchers at the Institute of Science and Technology in South Korea have developed a novel production technique of lithium-ion batteries that gets one step closer to direct electronics printing. And the particular battery can produce energy and cool at the same time. The team used 3D printing to produce a micro-channel system for supplying the battery with electrolytes. This system minimizes the need for pumping power and eliminates initial high temperature. In recent years, increased number of electronic components have become 3D printable, and in the near future, we can expect prototyping of smart, functional, high-tech devices developed for home. Next, Next, 3D printing is conventional power generation. What is conventional power generation? Conventional power generation is the general term applied to the production of electrical energy from coal, oil or natural gas using the stream. The generator is usually a machine having a small number of poles, 2 or 4, and running at a high speed 1500 and 3600 rpm revolution per minute. And electricity generation in the process of generating electric power from source of primary energy for utilize in the electric power industry. It is the stage prior to its delivery to end users, transmission, distribution, etc., or storage using and pump storage method. A characteristic of electricity is that it is not freely available in nature in large amount. So it must be produced, that is transforming other forms of energy to electricity. Production is carried out in the power station and also called power plants. Electricity is most often generated at a power plant by electromechanical generators, primarily driven by heat engines, fueled by combustion or nuclear fission, but also by other means such as kinetic energy of flowing water and wind. Kinetic energy of flowing water and wind. Other energy sources include solar photovoltaics and geothermal powers. And the main component, this is thermal power plant, is main components of the power plant. First is number one is cooling tower. This is cooling tower. And 2 is cooling water pump. Third one, 3-phase transmission line. Third one is 3-phase transmission line. And fourth, step up transformer. Fourth is step up transformer. Fifth is electrical generator. And 6, low pressure turbines, low pressure steam turbines. And 7th, feed water pumps. Next, 8 is surface condenser. And 9, this is intermediate pressure steam turbine. And 10th, steam control valve. And 11 is high pressure steam turbine. 11 is high pressure steam turbine. 9 is intermediate pressure steam turbine. And 6 is low pressure steam turbines. And next number is 12. 12 is deaerator. And 13 is feed water heater. 14, this is coal conveyor. And 15, coal hopper. 16 is coal pulverizer. And 17, boiler steam drum. and this is 18. 18 is bottom as hopper, and 19 is superheater. And this is 20 is fan, and 21 is reheater. 22 is this is combustion air intake, and 23 is economizer. This is heat exchanger. And what is heat exchanger? Heat exchanger is adiabatic device. Adiabatic device is no heat transfer. 23. 24 is 24. This is air preheater, and 25 is electrostatic, and 26 is fan. 27 flue gas, and 28 is flue gas stack. This is chimney stack. And this main components of the thermal power plant. Thermal power plant is conventional power generation. Conventional power generation is electrical energy from to generate the electrical energy from the coal. Next, 3D printing in conventional power generation. This is global energy data. And the US Department of Energy has been supporting the development of 3D printing for application in conventional energy. In July 2018, the Department of Energy selected 15 R&D projects for federal funding of $8.8 million to develop innovative technologies for fossil fuel power systems. In one of these projects, DNVGL plans to develop and validate support tools that optimize novel material combustions for fabrication, microchannel heat exchanger via additive manufacturing for supercritical CO2 carbon dioxide power cycle technology, providing new option for materials with property gradients for the fossil power industry. In other project, in United Technology Research Center aims to the application methods and tools to microstructure and mechanical properties for additive manufacturing nickel-based super alloy parts for turbine engines. In April 2018, achieves evaluation producing the first 3D printed metal replacement parts for an industrial steam turbine. According to the company, this is a game changer as it can be reduce the lead time for producing these parts by 40%. In 2017, completed its first full load engines tested for gas turbine blades produced using additive manufacturing technology. The company is in the process of developing additive manufacturing solution not just for turbine blades but also turbine vanes, burner nozzles, and radial impellers. The company Material Solution, a company in 3D printing in 2016, is investing 3D printing facility in the UK for Materials Solution. GE is also of the opinion that 3D printing is for the energy industry. The company has shipped 9,000 3D printed gas turbine components. The company further believes that 3D printing will enable it to enhance the efficiency of turbine in much less time owing to quick manufacture of prototypes and testing. An example of such components in the 3D printed fuel nozzles for the company HA class gas turbine. The nozzle helped the company push the efficiency of the turbines to 64% and is now working towards achieving an even higher efficiency of 65%. In 2016, inventor of electron beam melting machines for metal-based additive manufacturing and a producer of advanced metal powders helped GE gain the required expertise in 3D printing. Another benefit of 3D printing is that it makes the supply chain simpler by cutting costs. This is data for 3D printing in conventional power generation. Next, how does a thermal power plant work? A small video of thermal power plant. Next is 3D printing in the nuclear power industry. What is the nuclear power? Nuclear power is the use of nuclear reaction that release nuclear energy to generate heat, which most frequently is then used in steam turbines to produce electricity in the nuclear power plant. Nuclear power can be obtained from nuclear fission, nuclear decay, and nuclear fusion reactions. Presently, the vast majority of electricity from nuclear power is produced by nuclear fission of uranium, and nuclear decay processes are used in applications such as thermoelectric generators. Generating electricity from fusion power remains at the focus of international research. This article mostly deals with nuclear fission power for electricity generation. That is called nuclear power plant. And 3D printing in the nuclear power plant industry. This is global data energy. R&D is also ongoing to identify the application of 3D printing in the nuclear industry. In Feb 2018, Russia state-owned nuclear power utility, a company for a development of additive manufacturing technologies. It has already developed a pre-production prototype of a generation second 3D printer, the commercial production of which is scheduled for this year. In March 2017, Siemens successfully installed a 3D printed part, a metallic 108 millimeter diameter impeller for a fire protection pump in the Roscoe nuclear power plant. This technology can be used for parts which are no longer available and allowing old power plants to continue their operations, and is also using binder jetting additive manufacture in order to cut cost and cut short the lead times for parts that are different to obtain. This is global data energy. And how does a nuclear power plant work? A small video of nuclear power plant.
Nuclear power plants are thermal power stations which generate electrical energy from heat. They consist of numerous buildings and facilities, the most important of which are as follows. The turbine building houses several turbines as well as the generator necessary for electrical power generation. The containment building, where the nuclear reactor is housed, is made of meter-thick reinforced concrete. Inside this building, nuclear reactions take place where water is heated up. The cooling tower, which can be as tall as 200 meters, is where hot water is cooled. In order to easily understand the underlying principles, the following is a description of the most important components of a nuclear power plant that uses a pressurized water reactor, PWR. In the reactor pressure vessel, the nuclear reaction and the associated release of thermal energy takes place. In a pressurized water reactor, as in this case, the reactor pressure vessel stands about 12 meters tall. The walls are about 25 centimeters thick. Inside is where the fuel assemblies can be found. In pressurized water reactors, about 150 such assemblies are installed. A single fuel assembly is composed of many fuel rods. A fuel rod is about 5 meters in length and has a diameter of about 23 centimeters. The actual nuclear fuel is found inside of each fuel rod. Small nuclear fuel pellets composed of enriched uranium or plutonium make nuclear fission chain reaction possible. In the fission chain reaction, thermal energy is released. Water is needed in order to absorb the thermal energy and keep the chain reaction going. Inside the vessel, the water is heated to over 570 degrees Fahrenheit. The water does not boil, however, since the pressurizer maintains the water pressure constant at around 160 bars. The heated water is eventually pumped to a heat exchanger, also called steam generator. These are typically in the form of a shell and tube heat exchanger. Hot water flows through the U-tubes, heating up the metal of the pipes so that any water inside the heat exchanger begins to boil. The resulting steam is eventually fed through a set of pipes to the turbine building. The steam first drives a high-pressure turbine and then is typically fed to 2 low-pressure turbines. All of the turbines are connected by a spinning shaft to the electrical generator, which in turn produces AC electricity from the shaft's rotational energy. The steam is converted again into liquid form in a condenser, and then returned back to the steam generator. The water needed for this often comes from an adjacent river, or is cooled in a cooling tower. The water circulation systems are always kept separate from one another. Water in the primary circulation system never leaves the containment building. This water is radioactive, since it has been in direct contact with the fuel rods. Water in the secondary circulation system is used to drive the turbines and is not radioactive. The cooling circulation system provides cool water and is used to condense the steam in the secondary circulation system.
Next is 3D printing and power industry conclusion. 3D printing, a cutting-edge technology, is gradually finding its application in various facets of the power industry, including renewable and conventional power sectors and battery storage devices. However, as the technology is still in experimental stage and yet to achieve full commercialization, it will be a matter of time to fully understand how deep this new technology. In the power industry, given the high equipment standards required for efficient plant operation and the environment they endure. Next is screen printing to 3D printing of solar cells. In screen printing to 3D printing of solar cells, photovoltaic or solar cells have seen a rapid growth in the USA and the world in recent global photovoltaic shipments have increased 11 times in the last decade alone globally. Photovoltaic installation has reached 509 gigawatt, and this growth is driven in part by the availability of raw materials and PV technology and local government policies and crystalline silicon with 96% market share has been PV technology. Solar cells generate electricity in the presence of sun using photovoltaic effect. Photons, depending on their energy, generate electron hole pairs and charge carries. Solar cells have built-in PN junction for change separation. In conventional solar cells, metal contacts are placed on the front and back sides. To remove these charge, some advanced devices structure have metals only on a back side. And printing technologies face unique challenge as a solar cells become thin is less than 19 micron and lighter larger size, with demands on increased manufacturing throughout and lower manufacturing cost. PV industry has evolved from using contact printing techniques from contact to three-dimensional 3D printing of solar cells. In overview of the range of printing techniques such as screen printing, light induced plating and inkjet printing will be presented. This study will also discuss the market share of various printing technology. It will discuss the history of printing technology, single run and multi-run printing technology, additive manufacturing and market share of important contact printing technologies. Next is screen printing to 3D printing of solar cell. A small video of
Hi, my name is Brandon Rotondo. I'm with Devin McKenzie's group here at the University of Washington, and today I'll be walking you through the Solar X3 FOM roll-to-roll printer. So the main goal of this roll-to-roll printer is for us to be able to do flexible roll-to-roll processing of solar cells. The benefit of a roll-to-roll solar cell is that being able to be printed on plastic, you're now making a much lighter weight material that can be easily installed, easily mounted onto roofs, or because it's flexible, it can be placed onto many other surfaces. You can create semi-transparent solar cells, which allows you to collect light and at the same time also let some light through, which allows for uses in such as architectural windows where you still want to have light coming through to your room, but at the same time you could be harvesting energy to power low power electronics at the same time. So what we're printing here is a solar cell module. And in order to do that, what we do is we print multiple layers. So to start, we need a top electrode. in which case you can either use a transparent conductor or a printed silver grid, which will be done on something like the print station we have at the beginning of the roll. After that, we need to put down a electron or hole transport layer to add directionality to your absorber, so your carries don't recombine and you get efficient extraction. After that, we would be printing our active material, which we would be doing with the slot die coder. You could use organic polymers, organic dyes, or perovskite based active materials. After that, you would need to put down another transport layer, either a hole or electron once again, just whatever transport layer was not placed down beforehand. And that would be finally topped with a back electrode of silver to allow for maximum extraction of your cell without any concerns about blocking the light needed with the silver grid or transparent conductor on the front electrode. We start with an initial PET roll. This can be treated with either a transparent conductive oxide or be run as just plain substrate, depending on your application. The first step that we have to go through is rolling it and cleaning it to prepare the substrate for printing. So the first step is a static cleaner. We are discharging any static electricity and then using a rubber roller to pull off any particulates. The roll then travels through down to the corona plasma treatment to both clean the substrate and modify the surface energy to assist in printing. After the corona plasma treatment, we're ready for our first printing step. So the film will pass through, up, and into the first print station. The print station we have here is a screen printing station. With this, you can put down patterned films, patterned electrode contacts, allowing you to set up individual cells along your roll. One primary printing mechanism that we use is rotary screen printing, which is very similar to silk screen printing that you use in applications such as printing t-shirts. What this allows us to do is print high viscosity inks in fairly thick layers. We will use that for printing back electrodes of silver, where we want thick layers of highly conductive metal, and we want to be able to put down thick layers quickly. If we were to do the same process with something such as slot die coating, it would take up to 10 passes to get the thickness we can get in a single screen printing pass. After printing, you need to dry and anneal your films. So we move into our first oven. This is a 12-meter oven, allowing for residence times anywhere from 30 seconds up to 10 minutes. And we can run it from anywhere from 50 to 150 degrees Celsius. So in this oven, we take a multi-pass cycle through a spiral pattern to optimize oven residence time, as well as allow the film to maintain a upright position during the initial pass to prevent any runoff of your film. Coming out of the first oven, you can either run to a splicing table and roll up your roll as if you're done with your printing step, or we can move on to a second printing layer. In this case, we move on to a slot die deposition setup, which can be seen here. So the roll will go through the oven, through a few rollers to maintain tension and speed. Once again, we have a static discharge here available if need be. So in order to put down continuous films, we use a technique called slot die coating, in which a continuous curtain of film is deposited onto your moving substrate, allowing for uniform thin strips to be printed. The head that we have connected right now is a 13 millimeter stripe head, but we can do anywhere from 10 millimeters up to the full 300 millimeter substrate width. In order to slot die coat layers, we use a slot die head along with a syringe pump, so where we can put down a very controlled rate of deposition in order to determine our film thickness. If you look at the rate of the web moving through the printer versus the rate at which you're printing material, you can determine your film thickness.
depending on your height parameters.
To the web substrate, you can determine factors such as wetting or meniscus formation, which allows for printing of different viscosity materials. So once again, after printing in a slot die coating system, we need to dry and anneal our films. So we pass through a second 12-meter oven, following the same spiral path, allowing for maximum residence time in this setup. With a lot of solar materials, your anneal time is highly dependent, your efficiency is highly dependent on annealing time. And so we're trying to ensure the maximum amount of annealing per oven length. Once our film is passed through the oven, the film comes out and through, where we can now pass through a lamination station if we do have sensitive materials, such as UV light, water, or oxygen.
सर अभी रह रहा है.
हेलो, तो अभी ब्रेक कर दो सेशन, फिर 12 o'clock ज्वाइन करा लेते हैं.
ठीक है सर, ठीक है.
ठीक है, so we are breaking the session now. Please join again at 12 o'clock.